Okay. We are going to make solution. First of all, what is a solution? Solution is a homogeneous mixture of two or more substances. So if we have a sodium chloride in water, sodium chloride, it could be the solute if it's in the smaller amount, and water would be the solvent if it's in the greater amount. So if you have a 10% sodium chloride solution, then sodium chloride definitely would be the solute because it's only 10%, which is in the lesser amount compared to the water, which is like 90%. The water would be solvent in that case. When we talk about solution, let's look at some of the definitions for the solution, see what we have. Concentration for, so one is definition for solution. We talked about saturated, unsaturated definition and supersaturated last class. If the solution has less than maximum amount of the solute is going to be unsaturated. If it has the maximum amount, it's going to be saturated. And if it's less than or greater than the maximum amount, in theory, is going to be supersaturated. The other definitions we have, or terms, it could be concentrated solution or dilute solution. Concentrated solution means that it has a lot of substance in it, solute in it. If it's dilute, it doesn't have a lot, it's less of a solute in the solvent. But less or dilute or concentrated or saturated, unsaturated, it doesn't give specific numbers to a chemist or someone is trying to make calculation. It doesn't give you a specific numbers. If it doesn't give you a specific number, then they had to come up with the units that will give specific numbers. So the ratio of solute to solvent, it can be expressed in few different units. One of the units is percent of the solution. So percent could be percent by volume. So we could have a percent by volume, or we could have a percent by mass. So if you say percent by volume, what does it mean? Is it expresses the mass volume? It expresses the mass of the solute in given volume of the solution. So if it's a 10% mass volume, W for weight and V for volume, 10% mass by volume, that means that 10 gram of that solute is 100 milliliter of a solution, and this unit is very common. Okay, so it would be the volume of the solution, is not just volume of the solvent. The other unit would be parts per million. Parts per million, same thing as milligram per kilogram or milligram per liter of the solute. So that gives you the parts per million. So basically 1 milligram in 1 million milligram. 1 million milligram is 1,000 gram, or 1,000 gram is 1 kilogram. So milligram per kilogram or milligram per liter, it would be, the other name for that would be ppm. ppm, is used for, like, pollution is used for something that is very, very low. LD50, like for low lethal dosage, LD50. That means if you give that to, if you administer, if there's a poisonous compound or toxic compound, if you administer to 100 people, 50 will survive, 50 will not survive. So, so for very small numbers, they use ppm. Otherwise, like making solutions with the ppm, everyday life is not going to be easy, just measuring the mass of that much, very low concentration, or you may not even see that's how dilute it is, or how you may not even taste it if it's a ppm solution, but it has its own effect even at the ppm level if it's a toxic compound. The other definition is going to be molar solution. Molar solution it means number of moles per liter of solution. So molarity, it shows the unit for molar solution. And then we do have molality with an L, which we are not using in this lab. Molarity is a unit for concentration again. It shows number of moles of the solute per volume of solution. Wish I was able to write on this. I should be, but it looks like I'm not. Okay. So molarity, or mole per liter of the solution. Mole per liter of solution. So we need to know the number of moles. Now, how do we calculate number of moles? To calculate number of moles, we have to know the molar mass for the compound, which you need to calculate number of moles. I'm going to look at your responses. Sure, use the table, periodic table, very good, and find the molar mass, atomic mass for each of the atoms, multiply by the number of those atoms in per molecule, add them all up, there you have your molar mass for the compound. Then you use a balance or a scale in the lab to find how many grams do you need for certain number of moles, or if you have the mass, you divide by molar mass to find the number of moles. So to find number of moles, you need the mass of the substance and you need molar mass for the substance. So you can divide the mass by molar mass in order to get the number of moles. When you have the number of moles, then you divide that by liter of solution in order to get the concentration or molarity. So that's one way of making solution. If you have a pure solute, you can measure the mass. If you know you need like 5 moles, or if you need 0.5 moles, or if you need 1 mole or 0.1 mole, you find out how much is the mass for 1 mole, and then you find the ratio based on the ratio, how much would be the mass for 0.5 mole, and then you use the scale to measure that, which we are going to practice today. I just want to make sure that the concentration unit isn't, and it is covered in this case, which you have read the experiment already, but to make sure everyone gets where we are talking, when we are talking about molarity, where it's coming from, what does it mean? So moles of the other way to make the solution is like if you have a stock solution, if you have like concentrated solution, let's say you have concentrated sulfuric acid, you never measure the mass of sulfuric acid because you don't have it in solid or pure sample, but you do have the concentration for sulfuric acid, that is or you have the molarity. So in order to make a solution of sulfuric acid or hydrochloric acid, you need to know what is the concentration of the stock solution or concentrated solution, and then how much of that solution you want to make. The relationship is like molarity times volume. Molarity times volume is the same thing as number of moles. Molarity times volume for before diluting equals molarity times volume after diluting. So basically, if you have a cup of or glass of sweet tea and you think that it's too sweet and you don't want to drink that much sugar, or you don't want to eat that much sugar, then you say, I'm going to add some water. If you add water and you only drink half of it, you did cut the sugar in half. But if you dilute it and it tastes less sweet, but you drink both glasses of the sweet tea, instead of 1 glass, now you drink 2 glasses, the sugar intake is still going to be the same. Basically, the sugar doesn't go anywhere, and you don't increase the sugar, you're just adding water to make it taste less sweet. If it tastes less sweet, that means it's diluted, is less concentrated, but the total number of moles or number of particles, it doesn't change, so it's the same. So anytime you have the molarity, which is the concentration, times the volume, that gives you number of moles. Number of moles is going to be constant before diluting and after diluting. Okay, the laboratory for the calculation now. So we need to know we should have either the solution, a concentrated solution, so we find out how many milliliters of that we need to get in order to make the new volume of the solution with the concentration. So basically you have four variables here. You have the molarity, you have volume. Before diluting, you have molarity and volume after diluting. So three of them needs to be known to you, and you can find one. So it's an equation with four variables. Three of them should be given to you, and one you just find it by solving the equation. For the calculation, we have an example of calculation. How many grams of solid sodium hydroxide are needed to prepare 200 milliliter of 4.00% by volume of sodium hydroxide solution? Now, if you say 4%, what does it actually mean? 4% solution, it means 4 grams of sodium hydroxide in every 100 milliliter of the solution, right? So you have a ratio. For every 100 gram, you have 4 grams of sodium hydroxide. If you want to make 200 milliliter, how many grams do you need? It's going to be 8, because for every 100 milliliter, you need 4 grams. Now for 200 milliliters, you calculate this and you get 8. The other problem, it says how many grams of solid sodium hydroxide needed to prepare 2 liters of 50 ppm sodium hydroxide solution. Is there any question about the first problem example? Okay, perfect. The second example is the ppm, and that means the 1 milligram in liter or milligram per kilogram. If you just since you know what it means, then you can find the ratio. So for every 50 milligram, you could find in every liter. So if you want to make 2 liters of that, it's going to be multiplied by the 50. 2 times 50, the units of the liter is going to cancel, and you end up with 100 milligram or 0.1 gram of sodium hydroxide. So this is still theory, because we can do all of this without being in the lab, right? I just want to make sure that we know how to do the calculation before we use those masses in order to find the I got your email also about that problem. Let me see. The question was asking, because I changed the numbers for the question. I changed it from the numbers that it was there to new number. I didn't remember the new number. So since I didn't know the new number, I couldn't answer your email. Now that I know, we can review that question to make sure that these are the exact numbers that you have on the question. And if these are the exact number you have on the question, then 10 is going to be the correct number. And if I chose the wrong answer, then I will regrade those questions. Okay, so I will make sure that I will grade it again. So I will pick the right answer, and then I go back and I update the grade. So no problem. Sure. Okay, I'm going back to the other page now for how many grams of solid sodium hydroxide needed to prepare 500 milliliter of 0.15 molar solution. So if it's 0.15 capital M, that means it's 0.15 mole for every 1000 milliliter. And you can find out how much do you need for 500 milliliter, since, okay, so this is going to be 500, the milliliter is going to cancel, you end up with number of moles, but you can't use the mole, you have to convert the mole to gram in order to have a usable number in the lab, because you're dealing with the balance and actual compound. So you have to multiply by molar mass. So you find the number of moles first, then you multiply by molar mass in order to get the mass of that substance. Okay. How many milliliters of stock solution? When you say stock solution, that means it's more concentrated, and by diluting, by adding water, you are going to make it less concentrated, or you lower the molarity. So basically, molarity of the 6 molar solution times the volume of the stock solution equals 500 times 0.3. Then you can find the number of milliliters of the solution needed for the. Okay. Now let's move to actual experiment. And before I go over your quiz questions, yes, the 3 on the in the question is a KOH. If it's a KOH, you multiply by 56 instead of the 40 that is for NaOH. So that should change the answer, okay? But I will go ahead and look at the quiz after we are done with the experiment. Okay? It's possible. Yes, because the molar mass for the compound, it's different, so we have to find it. So I have to open the question, and then we will review the question together after we are done with the lab. But for now, let's go ahead and measure the chemicals that we need for the experiment. Okay, we need to make 3 solutions from sodium nitrate. If we want to make, we have the pure solid for sodium nitrate. Can you tell me based on your calculation, how many grams do we need for the 500 milliliter of 0.02% by volume? How many grams of sodium nitrate do we need for the first solution? 10 milligram? Okay. 0.02%, so it would be 5 times 0.02. Point 0.1 gram, right? 0.1 gram. Okay. 0.1 gram, that is going to be 100 milligram. Is that right? 100 milligram. So I'm going to write down somewhere. We need the 100 milligram for the first solution. Because I have to do the calculation first, and then I close the document that I'm sharing with you, the experiment. Then I go for the actual lab. So first, 0.1 gram. This is for the first solution of sodium nitrate. For second one, we need 1,000 milliliter of 400 ppm. How much do we need? What mass for the second one? Do we need 400 milligram? Yes? 400 milligram. 400 milligram in 1 liter, and since we want 1 liter, then it's going to be 400 milligram. Very good. 400 milligram of NaNO3. This is for 1 liter. The first one is a 500 milliliter. And 25 milliliter of 0.1 molar NaNO3. So what is the final answer? What do you have for the molar mass of sodium nitrate? No, we are looking for sodium hydroxide. I'm looking for the problem number 3. 185, is that correct? Can you give me the molar mass, please? Molar mass for sodium hydroxide is 23 plus 14 plus 48, right? Nitrogen is 14, yes. 23 plus 14 plus 48, okay. 23 plus 14 plus 48, that gives 85. And 85 times 0.025, right? 85 times 0.025. No. $250 times 0.1, 25 divided by 1,000, 0.025 times 85, 2.125, and that is grams. Okay. Yes. So for 3, we need that, and that's for 250 milliliter. So we have the volume and we have the mass. Okay, we are going to make these 3 solutions. What's the next step for your experiment? After we make those 3 solutions, since we did the calculation, we are going to make those solutions. Then we are going to use the machine, and using the machine, we will find out if the solutions that we made, they are okay or not. We also need to do the calculation, and we make solution number 4 by dilution. And for solution number 4, we want to make 500.005 from 0.1 times volume. So divide both sides by 0.1. So 500 times 0.005 divided by 0.1. Volume is 25 milliliters, right? Is that what you find? And you want to change that to 500 milliliter. Okay. That's it. So we have 4 solutions, and with the 4 solutions, we need to prepare the 4 solutions. And after we prepare the 4 solutions, we need to measure the nitrate concentration using the probe. Okay. Any questions before I start the experiment? Perfect. Okay. Now we have the numbers of the solutions. The first 3 solutions, we are going to just measure the mass that we calculated, and we need to, okay, going to measure the mass and I show it to you, hopefully. Just have to trust me based on the numbers. If I move this, I'm using a different laptop today, so I was hoping I can write on it on the page because it's a surface, but still I cannot write. Okay. The first one is 500 milliliter. Okay. We are going to make a solution, 500 milliliter solution. The volumetric flask is one of the accurate equipments for measuring device to measure the volume, just like the pipettes that we looked at it before. It has like an index line and it has a number, and when you fill up the solution or the container up to the index line is going to contain exactly, if you adjust the meniscus, is going to contain exactly 500 milliliter. Because we are making solution, we cannot use a beaker and let's say measure 500 milliliter of water and add to it. The volume of the solute is included in the volume of the solution. So the solute plus the solvent, it should add up to 500 milliliter. Sometimes you add the solid and the liquid, you make it to 500, you mix it, it's going to drop. So it's better first to dissolve it with about, and it's very hard to shake it to mix it well. So it's better to dissolve with the lower volume of the solvent, so you can shake it well, make sure that you have a homogeneous solution, then raise to the volume. So we are going to measure the solid first, the 0.1 gram, you said, right? We calculated 0.1 gram. So tiny. Okay, I have the 0.1 gram. Transfer into the flask, volumetric flask. We are going to add water. Going to add water to 2/3 of the flask. I added enough water to be able to shake it, mix it well, and dissolve the sample in. After the sample is completely dissolved, then I'm going to add enough solution, enough solvent, or add, basically the next step is add enough water to raise to the volume to make sure that it reaches to the index line. Let me change my wash water, maybe this one looks better. I have to be very careful adding the last few drops. It has to be very slowly so I do not pass the meniscus or the index line. Basically 1 drop at a time. Okay. Meniscus is at the level of the index line. Now, if I don't mix it well, the top portion is going to be less concentrated than the bottom, and that is going to affect, when I'm taking solution, the density or the concentration on top of the solution is not going to be the same. When I have the volume already fixed, now I'm going to turn it upside down and make sure that is mixed well. Okay. Make sure that is mixed well. Okay. Now, solution 1 is ready. So before I make any mistakes, I need to label that. This is solution 1, the first solution 1. So I made the solution 1. Solution 2. So what's the concentration of the solution 1? Do you remember the concentration? What's the percentage? 0.02%, okay? 0.02%. And for second one, is it 400 ppm, the second solution? 400 ppm, okay. 400 ppm, second one. Let's make the second solution 400 milligram or 0.4 grams in 1 liter. So if I want to make 1 liter solution, now I have to change my volumetric flask. I'm using 1000 milliliter flask. Measure the 0.4 grams. Okay. I have measured 0.4 gram exactly. Okay, using the scale, I measured exactly 0.4 grams. Now I'm going to transfer that to the flask. Transfer the 0.4 grams into the flask, the 1000 ml or 1 liter flask. What's my next step? What should I do next? I have the solid, which we did the calculation, and added to the flask. What should be my next step? Okay, volume. So what does it mean? What should be my next step? Are you answering me, or what should be my next step? I have the solid. How much of deionized water should I add? How much DI water should I add? How much? 2/3. Okay. I need to add 2/3. Add enough water to get to the 2/3. Okay, 2/3 of water is being added. Next, what should I do next? Stir it to dissolve, okay? Then I have to mix it well to dissolve. And what's my next step after it dissolved? Sodium nitrate, just like potassium nitrate, it has high solubility, so it dissolves fast in water. What should be the next step? Continue adding water slowly to get to reach the index line, or to the line that indicates we have exactly 1 milliliter of solution. One liter of solution, sorry. 1 liter of solution. Okay. The index line right here, I'm going to add enough water drop by drop to make sure that the water, the meniscus is going to be on the exactly on the index line. Okay, aligns with the index line. Then we just mix it well a few times to make sure that solution is uniform, because that's the definition for solution. Solution is homogeneous and uniform mixture of two compounds, two or more substances. So when we say it has to be uniform or homogeneous mixture, that means you cannot have high concentration down here and low concentration up here, because we are adding more water later. If this area is denser, it's going to have high concentration. So you have to mix it very well in order to make sure that you have your uniform solution. Okay, next, let me label that too. Got to make the solution 3 now. For solution 3, you have 2.125 grams in 250 ml. So using the 250 ml, this is solution 3. Going to measure the 2.12 grams. Okay. Measure the 2.125 grams. Transfer into 250 ml flask. Perfect. Add water to 2/3, right? Add water to 2/3. Mix it well to dissolve. Okay. After it's dissolved, now I'm going to add forgot my glasses. Sorry. Going to add more water to volume. That means the level of the liquid should reach the index line. So I have to add very slowly. Going to add the last portion of it, 1 drop at the time, until it gets to the meniscus line. Okay. The meniscus is at the line. I have to make sure to mix this well. So the first 3 solutions are made. Now I have to make a next solution, which is 0.005 molar from 0.1. We already did the calculation for next solution. For solution 4, what should I do? What does that 25 milliliter means? The calculation we did for 4. You found 25 as the answer for solution 4. What does it mean? What should we do from there? To make the solution 4, what are my steps? Do you know the steps for solution 4? What are you trying to make? Read it again, please. What are you trying to make? Your solution 4. We did the calculation for it. What are we trying to do with the 25 milliliter that we found? Okay, we take 25 milliliters of the 0.1. Okay, we take 25 milliliters of the 0.1, and that was the solution 3, right? So volumetric flask 3 had the 0.1 solution, 0.1 molar solution. We take 25 milliliters of that, and we place that 25 milliliters of the solution into a volumetric flask that is 500. It's volumetric flask. The size of it is 500 volumetric flask. So I would use this 25 milliliter transfer. We need to add DI water to dilute this 25 milliliter. So basically, we are diluting the 25 milliliter of concentrated solution in order to lower the concentration to 0.005. Okay. And that is the solution number 4. I like to label it so I don't get confused later, because we have 2 of these flasks, flask 1 and flask 4. They are both 500 milliliter. Now we are going to add enough. Add some water first and mix it well. We're going to add 2/3. Mix it well. I have to mix this well before I mix well. And now I'm going to add more to reach to the volume of 500. Okay. Four solutions are prepared. I'm going to use the program to also determine the concentration of the nitrate. I just hope that the program works. So help me with this, please. The 0.1 gram I have my 4 solutions, and going to measure the concentration one at a time. Okay. The solution for 100 milligram per liter is empty. I hope we have more of that, but we have at least 1 milligram per liter for low concentration. To ask if we can get the other one. Okay. We're going to pour the solution into 50 ml beaker and calibrate. So first, I want to make sure that if I'm using the 1 milligram, this is a standard that is going to actually read 1 milligram. So the size of the beaker really doesn't matter as long as the cell stays in the solution. So we could use the 50 milliliter beaker. This is the standard. This is just trying to calibrate the solution. And hopefully it works. Okay, that is 1 milligram. And okay, perfect. Next, which solution should I use next? Does it matter? The 0.02, the first one then, solution 1. Okay, gonna use the solution 1. This is the 0.02, and I want to see if it's going to read or not. Hopefully it is the right number. Okay, it didn't read the 0.02. Going to try the next solution. See, I think one of the solutions they were if the deionized water that I used to make the solution had any nitrate, it wouldn't read. So it's less likely that we get an accurate number here, but I want to try all of them to see at least if it's going to show me the high or low concentration. For solution 2,
We'll talk about this. So this is middle, but there's
okay.
no high and low.
Okay, thank you. Thank you. Okay, the probe, I'm not sure why is not working. So anything that I use is just giving me 1 milligram per liter. Looks like the DI water that we are using, it already has some nitrate. So because it's not working, the interface, everything is working, I mean, is connected. The program is running, but is not showing the correct concentration. So I'm going to see if I can get a different deionized water, and I make these solutions. You already learned how to make the solution. That was the main part of this lab, to learn about the steps, being able to do the calculation, being able to use the volumetric flask. When you are making solution, first you have to dissolve it with 2/3 of the solvent, dissolve it well completely, and then you add enough water to get to the index line. And when you have it, then you have to mix it well so the solution is uniform. And you learn how to make solution from concentrated solution. So basically that is you are going to calculate how many milliliters of concentrated solution you have to make the new volume of the dilute solution. Again, using volumetric flask, you are going to dilute it to the new volume. Concentration would be lower when the volume is high, and concentration if the volume is low, concentration would be higher. So when I get these working, because now I have to find a different standard that is in the same level, and find a different DI water. So there is no contribution from the DI water. I'm going to email you those numbers, and you can do your report based on those numbers. And I should be able to do that before noon tomorrow. When the lab manager is here, I would repeat the experiment by myself, and I will send you those numbers. So for now, the chart is going to stay empty. The theoretical part, you are going to complete it. You learned how to make solution because that is the purpose of this experiment. And testing with the machine, it was to find out that you did the procedure properly or not. But you were all, you're all witness that I had measured the volume and the mass and did the calculation all together. So the only problem is the DI water. So I will make sure to repeat this experiment with different deionized water to make the solution, and I get you those numbers or reading from the machine tomorrow before noon. Screenshots. To take a screenshot of this, because I was using surface, it's not very convenient. This is like very fragile. It drops. I didn't want to make it because you could take a screenshot of this setup, and then take a screenshot also. Okay, you could take a screenshot of this setup here, and also take a screenshot of the 4 solutions. Let me turn around with when the numbers are visible. Okay, take a screenshot also of the 4 solutions with the labels. You have the numbers. Take a screenshot, please. Those 2 screenshots should be sufficient. Any questions from this experiment, the experimental part? Sure. Yes. All I'm going to do, I'm going to put the samples and read it the same way I did today, but hopefully with the different DI water, I would get more accurate reading, because the reading for all samples that I use now, they were same reading basically. It didn't make the difference when I used low concentration or high concentration. So basically, it was reading the nitrate from DI water. It looks like it. So the experimental procedure, it would be the same as what I did today. The only difference is the value for readings. So you only need the value for reading. So before noon tomorrow, I will give you those numbers, or I will send you an email if it didn't work. The theoretical value, it should be the concentration that you have, the milliliter per liter of nitrate that you made the solutions. Yes, is what you calculated. The theoretical value is based on the calculation. So if you have the percent, 0.02%, that's 0.02 gram in 100 gram, then you have to change that to 0.02 gram. How much is going to be in 1 liter, right? So you have to change that to milligram in liter. So just be careful of the units. The 400 ppm is going to stay the same, because that is the milligram per liter. So exact same numbers of the concentration that you have expressed in milligram per liter. Any questions about this experiment? And also find the theoretical value for milligram per liter for each of the solutions, please. Is the question how to go from percent to milligram per liter? If that is the question, then what you do, you just look at the definition. What does percent mean? Percent means that you have gram per 100 milliliter. Okay, percent is, that's in gram in 100. So is a 0.02 gram in 100 milliliter. So you change the 0.02 gram to milligram. So that's going to be 20 gram in 100. So how much is going to be in 1000 milliliter or 1 liter? Basically, it's the conversion factor. So all you do is just convert it. Uh, 0.02%. What does this mean? It means 0.02 gram in 100 milliliters. Is that correct? So you want to change this to, you want to convert to milligram, the top one. So it's going to be 1000 milligram over 1 gram. So the gram is going to cancel. And you want to change this to liter also. So this is going to be 1000 So the milliliter has to cancel. 1000 milliliter over 1 liter. So you end up with milliliter being canceled and gram would be canceled. Your final answer is going to be whatever you find for the final answer. So this is going to be 200. So it's going to be 200 milligram per liter. Is that right? Okay, so that's how you convert from 0.02% to milligram per liter. And same thing for the others. Second one is already 400 milligram per liter. And then let me look at the table again. Just want to see what it's asking for. There's one that it says you don't have to do it. Okay. So for theoretical value, the first one is going to be 200 milligram per liter. Second one is going to be 400 milligram per liter. Third one, you don't have to measure it. And the fifth one, the molarity is 0.005. Molarity is 0.005. Then you have to convert that to gram. So if I answer all that questions, then basically I have to grade myself, right? 0.005 capital M times 85 grams over 1 mole, because this is for sodium nitrate. So you change this to gram. And this is mole per liter. So all we have to do is just gram. So when you find the gram, then you want to find it to, if you want to change it to milligram per liter. So times 1000 milligram over 1 gram. So what you need to cancel here, you need to cancel the gram. You need to cancel mole. What you end up with is going to be milligram per liter. So you just have to do the okay. 425 milligram per liter, perfect. Okay, any other questions for this experiment? Okay, perfect. So that's like changing within the units. Any questions for this experiment? Okay, I'm going to stop recording, and then I will talk about the quiz, because I don't want the quiz questions to come on the recording.